Write down the heading. Group 2, which is Alkaline Earth Metal. Yeah, 1 second. Done? Okay. Okay, see the group 2 elements, we also have the same kind of properties. What difference we have, that we'll see obviously. But like in general thing, top to bottom, if you go, electronegativity decreases, size increases, ionization enthalpy decreases. These kind of properties are same over here, right? It is not going to change, right? It's very simple and same we have. Okay, so what all elements are there in group 2? The elements which are present in group 2 are, we have beryllium, magnesium, calcium, strontium, barium, and last one is what? Radium. Francium is in group 1, Kshitish. Okay, these are the compounds we have. If you look at the electronic configuration here, beryllium has 4 electrons, atomic number 4. So it is 1s2, 2s2 configuration. Okay, belongs to the second period. Magnesium belongs to third period, atomic number 12. So it is 1s2, 2s2, 2p6, and 3s2. Similarly, for calcium, it is 4s2 outermost configuration. Strontium, it is 5s2, and so on will go. Right. So the general outermost electronic configuration is ns2. Can we say that? Like for the first, group, we have ns1. Here, general EC, electronic configuration, general outermost electronic configuration is ns1, right? One electron, sorry, ns2, I'm sorry, ns2, where n is the period of the element. Okay. If you talk about some general properties, like if I say atomic and ionic radius, in short, I'll write down, okay, because we have discussed these things in group 1. So atomic radius and ionic radius. So we know as we go down the group, one extra energy shell is getting added, right? And hence down the group, atomic and ionic radius increases. As we go down the group, atomic and ionic radius increases. Increases. Okay, both. So down the group, size increases. Size increases, so ionization enthalpy. Tell me. Ionization enthalpy decreases. down the group. Okay. If you compare this with the first group of element, so for group 1 you see the electronic configuration is ns1, and for group 2 the electronic configuration is ns2. So if you compare the first ionization energy, because of its stable configuration, the IE1 first ionization energy of the elements of group 2 is greater than to that of group 1. Understood this? This order you understood? No doubt. If you compare IE2 for group 2 and IE2 for group 1, what would be the order? IE2 for group 2 and group 1? If you look at the configuration of IE2 of group 2 and group 1, group 2 will be lesser because group 1 has stronger or stable configuration. So order is opposite over here. Okay. Even if you talk about the ionic size, so the ionic size of group 1 element is more than to that of group 2. Left to right as we go in a periodic table, we have discussed this in periodic properties. Left to right, effective nuclear charge increases, ionic radius decreases. So group 1 elements are relatively more in size in comparison to the corresponding group elements of group 2. Got it? Okay, so these two properties we have. Now, when you talk about the oxidation state, third one, second is what? Achha, second order that did I read it other way? Let me check this. It is other way around. Yeah. By mistake. So it should be this. I2 of group 1 is more than to that of group 2. Yeah. So next write down. Third one is the oxidation state. What is the possible oxidation state for the elements of group 2? The possible oxidation state of elements of group 2 is +1 and +2. Obviously, the +2 is more stable oxidation state. Okay, so write down alkaline earth metal shows a stable +2 oxidation state shows stable +2 oxidation state stable +2 oxidation state okay, because 2 electrons in the outermost shell, so it can easily lose the 2 electron to gain the stability. Correct? So this is what we have. We can also understand here bond hypercycle that we have already discussed in periodic properties. Okay. Write down one note here. The second ionization enthalpies of alkaline earth metal. The second ionization enthalpy of alkaline earth metal is almost twice of first ionization energy and hence they form bivalent molecule. Hence they form bivalent molecule. They form bivalent molecule rather than monovalent compound. The reason is simple. When it loses 2 electron, it has the stable configuration, inert configuration, and hence it forms these compounds, right? Yeah, so oxidation state is +2 possible. Okay. Melting point and boiling point to write down. Oh, wait, first write down electropositive character. As we go down the group, what happens? Electropositive character. Electropositive character is what? The tendency to form the positive charge ion, right? So we know as we go down the group, the ionization energy decreases, the tendency to lose electron is more, right? And hence the electropositive character increases, right? So write down as we go down the group, electropositive character increases. So the order is beryllium, magnesium, calcium, strontium, and then barium. Electropositive character. And the same thing we have for metallic character. Electropositive nature. And also we have this for metallic nature. Okay, both increases down the group because ionization energy decreases. Okay. Some physical properties we see. Write down melting point and boiling point. Melting point and boiling point. Write down. The melting and boiling point of alkaline earth metal the melting point and boiling point of alkaline earth metal is higher than is higher than to that of the corresponding is higher than to that of the corresponding alkali metals. Okay. And what is the reason for this? Melting point and boiling point? Write down. One more point to write down after this. We have just discussed that alkaline earth metal will have higher melting and boiling point than alkali. What happens as we go down the group? Okay, so write down the next line. As we go down the group, the metallic bond strength decreases. Metallic bond strength decreases. Hence, in general, the melting and boiling point decreases. In general, melting and boiling point decreases. But there is no regular trend here. Means in general it happens, down the group decreases, but in case of alkaline earth metal, there is no general trend. Okay, the trend is irregular, sometimes decreases, increases, and like that. Okay, but if you talk about alkali metals, so for alkali metals down the group, the melting point, boiling point decreases. Reason is metallic strength decreases, bond strength decreases, right? But if you talk about group 2 elements down the group, there is no regular trend in the melting and boiling point of alkaline earth metal, right? 2 3 reasons are there: different size, different structure that they adopt, plus the metallic bond strength also we have. Okay, however, what you can keep in mind, beryllium, if I write down the values here, you see, for beryllium, the melting point is, I'll write down the two table here: melting point and boiling point. Melting point, boiling point, both are in Kelvin. Okay, in general, just one thing you have to memorize. Like you see, if you talk about beryllium, for beryllium, the melting point and boiling point both are maximum. 1560 is the melting point, and 2750 or 45 is the boiling point. Okay, then we have magnesium, calcium, strontium, and barium. So for magnesium, it is 924, and this one is 1360. You see, it becomes almost half the value, right? Then again, it increases 1124. For this one, again, it increases 1763, 67. Then it is 1062. It is 1655. It is 1002 and 2078. So obviously these values you don't have to memorize, but You see the boiling point order is important here. Beryllium has maximum, and then we have barium. Okay, after beryllium, we have barium. These two things you must remember. Copy this down. Okay, so this is the trend we have for melting and boiling point. They don't ask you the entire trend, but sometimes, yes, they may ask that which one has maximum boiling point or minimum boiling point, something like that. Okay, but we don't have any irregular trend over here. Okay, now the thing is next here, that is hydration enthalpy. Hydration enthalpy is important. Okay, so next write down the sixth point. Hydration enthalpy. Write down as we go down the group, as we go down the group, the hydration enthalpies of alkaline earth metal ions decreases. Okay, as we go down the group, the hydration enthalpies of alkaline earth metal ions decreases. So the reason is, write down, as we go down the group, like what happens here, down the group, size of the metal ions means M+2 ions increases. Size of M+2 ion increases. As a result, what happens? The charge density decreases. What is charge density? And hence degree of hydration decreases. And hence degree of hydration decreases. Charge density means charge per unit volume. Okay, charge divided by volume of the ion, metal, whatever it is, that is charge density. Whenever you see density term is associated with charge or something like that, then we always consider per unit volume. Correct. Sometimes they also write charge per radius ratio, which is nothing but the same thing. Like terms are different, but a result will be same if you consider volume or radius ratio. Okay. One note you write down, the hydration enthalpy. The hydration enthalpy of group 2 ions is 4 to 5 times greater than 4 to 5 times greater than to that of group 1 ions. Okay. Next, write down the nature of compounds. Nature of compound formed. So elements of group 2 predominantly forms ionic compound. Okay, it forms ionic compound. Hydrogen also we have seen, they forms ionic hydrides. Okay, if you remember, ionic compounds they form. Reason is due to their low ionization energy. Due to their low ionization energy, it can easily lose electron and forms ionic bond. Now the ionic character write down. As we go down the group, the ionic character increases. Why it happens? Any explanation for this? Why ionic character increases as we go down the group? Yes, a smaller cation can polarize an ion, right? And hence the Fazan's rule, the polarization decreases as we go down the group. Polarization decreases and hence the ionic character increases, because we know polarization leads to the ionic character in the compound. Write down one note here. Beryllium compounds in anhydrous form when there is no water of crystallization, in anhydrous form are covalent in nature. But on hydration, it becomes ionic. Reason is very simple. In anhydrous form, the charge density of beryllium ion is high and it can provide high polarization, right? So write down, in anhydrous form, the charge density of B +2 is high, and hence it provides high polarization, which leads to covalent nature. So whenever the question is about this thing, ionic and covalent, you can think of Fazan's rule, simple. Okay. You must have the option, with option and then Fazan's rule, you can find out the best possible answer that you could have. Correct? So always take care of that, especially in S block. Okay, here the Fazan's rule valid. Because if you remember, Fazan's rule is valid only for ionic compound, right? Perfectly covalent compound like CH4 and others, Fazan's rule are not valid. Okay, in ionic compound only we can say the percentage ionic or percentage covalent character, whether it increases or decreases down the group or not, right? So in S block, for this thing, ionic and covalent concept, you can think of Fazan's rule. Keep that in mind. Okay. Now, next write down solubility and lattice enthalpy. Eighth one. Solubility and lattice enthalpy. Write down lattice energy of group 2 elements. Lattice energy of group 2 elements is much higher than to that of group 1. Lattice energy is much higher because the size is less. Okay. So lattice energy of group 2 elements is much higher than to that of group 1. Okay. Reason I said because of size decreases. Write down for alkaline earth metal, as we go down the group, as we go down the group, lattice enthalpy and hydrogen enthalpy, lattice enthalpy and hydration enthalpy decreases as the size increases. So if lattice energy decreases, this means what? Solubility increases. So solubility and lattice energy is inversely proportional. Inversely proportional to lattice energy. More lattice energy, easy to break, difficult will be to break the bond, and hence solubility will be less. Okay. Done. Okay. Next, write down. We'll see, the different types of compounds that these, elements forms. That is the, nitrites we have, oxides we have, hydroxides we have, hydrides, all these things, correct? Carbonates, bicarbonates, all these things. So write down first of all, chemical reactivity. Chemical reactivity. Again, as we go down the group, size increases, ionization energy decreases, tendency to lose electron is more, it can easily form +1, +2 oxidation state, and hence the reactivity increases. So reactivity order is minimum for beryllium, magnesium, calcium, strontium, and barium. This is the order we have. Okay, chemical reactivity. Again, like I said in the last, this thing after class, that first element of all the groups will have some abnormal properties, abnormal behavior, and that is true and valid here also. Beryllium will have some abnormal properties here. First reaction we are going to see here, that is reactivity towards air. Towards air. Write down due to increase in electropositive nature. Write down like this, as we go down the group, the electropositive nature increases, and hence reactivity towards oxygen also increases. Towards oxygen increases. Among all these elements, beryllium and magnesium does not react with oxygen easily. Okay, they forms an oxide layer on its surface, and hence the further reaction is hindered. Okay, but at higher temperature, the reaction possible. Okay, so write down this point. Beryllium and magnesium, Be and Mg, are kinetically inert towards oxygen due to the formation of a thin oxide layer. On its surface. Kinetically inert means the reaction rate is negligible, it's extremely slow. Kinetics means, the flow of reaction, how the reaction proceeds. So kinetically inert means the reaction rate is extremely slow, and we ignore that. Like, okay, the reaction is very difficult to proceed because of the low rate, and hence we ignore that. Means it's not like the reaction is not happening. Rate of the reaction is very slow. Clear? Okay. So this is important for beryllium and magnesium. But at higher temperature, write down. But at higher temperature, they reacts with oxygen and nitrogen, atmospheric oxygen and nitrogen, forms oxides and nitrides. So what type of oxides and nitride it forms, that is important. For example, you see 2Be plus O2 from air, it gives BeO. The temperature we are using 873 Kelvin or more than this for this reaction to proceed. With nitrogen, you see 3Be plus N2. Again, this is from air only. It converts Be3N2, beryllium nitride. Magnesium also, you see, reacts with 2Mg plus O2 in presence of air. When we heat this, it converts into 2MgO. 3Mg plus N2, it gives Mg3N2. Done. Which chapter is going on in school? It's a redox. Thermodynamics? Okay, fine. Next, write down reactivity towards water. Here also you see the reactivity increases down the group, and all these metals reacts with water and forms hydroxides of MOH whole twice, and hydrogen gas eliminates you. H2, 2H2 we are taking. This is the general reaction we have. Remember, first group 1, it forms MOH type hydroxide. Here it forms MOH whole twice because the valency is 2. Right? So again, you write down reactivity decreases down the group. right? Could you tell me the reaction of alkali metal with water, exothermic or endothermic? Exothermic or endothermic? Exothermic. High amount of energy releases. Correct. Okay. Same thing we have here also. Okay. But the amount of energy releases is lesser than to that of group 1 element. Okay. Right on this point. The energy releases, this you write down here, it is exothermic first of all, plus heat. And then the energy releases is lesser than to that of alkali metals. Hence, the reaction is less vigorous. Two very important points to write down in this note. First point, beryllium since forms oxide layer on its surface, beryllium since forms oxide layer on its surface, oxide layer on its surface, does not react with water, does not react with water, does not react with water at all, does not react with water at all. Next line, magnesium also forms oxide layer, protective oxide layer. Magnesium also forms protective oxide layer. It does not react with cold water. It does not react with cold water. But it can react with water at high temperature. So basically at high temperature or boiled water, the oxide layer breaks down. Okay, and the reaction possible. So beryllium does not react at all. Magnesium not with cold water, but reacts with hot water or boiled water. Okay, all other elements are simple. They react with water as it is. Reactivity, we know it is as you go down the group, reactivity increases. Okay, we already know about hydrides. Okay, just to write down quickly, reactivity towards hydrogen. We know these elements reacts with hydrogen and forms hydrides of MH2 type. Okay, all these hydrides are ionic in nature, except what? Except, yeah, tell me. BeH2 and MgH2. BeH2 and MgH, the first two elements, they are covalent. Because of the small size of cation, more polarization, covalent nature is there. Done. Next, write down reactivity towards halogen. Reactivity towards halogen. Write down elements of group 2 reacts with halogens at elevated temperature. At elevated temperature and forms halide of mx2 type, halides of mx2 type. So the reaction is any element m plus x2. We heat this and it forms mx2 halides. We can also get halides when metal reacts with HX. Okay, it forms mx2 plus H2. When metal oxide MO reacts with 2HX again, it forms mx2 plus H2O. Carbonate, if you see, M2CO3 plus HX, sorry, HX, it forms mx2 plus H2O plus CO2. Hydroxide, if you see, MOH twice plus HX, 2HX, it forms MX2 plus 2H2O. Done, copied. Okay. One more reaction here, write down. Write down reactivity towards acid and base. reactivity towards acid and base. Elements of group 2 reacts with acids and liberates hydrogen, H2. Metal M reacts with, suppose, H2SO4, forms MSO4 plus H2. Same thing we can write for HCl also. For concentrated HNO3, if you see, M plus HNO3 gives MNO3 twice and H2, hydrogen gas evolves. This happens when HNO3 is very dilute. The reaction is important for HNO3. If any metal reacts with HNO3, but this HNO3 is not dilute now, not very dilute now, concentration of HNO3 also matters a lot in this reaction. Very dilute eliminates H2. If you take dilute acid, then it evolves nitrogen monoxide gas. 3 Mg NO3 whole twice plus 2 H2O plus H2. Sorry, 2 H2O plus 2 NO. MgNO3 whole twice plus H2O plus NO. Nitrogen monoxide evolves in this. So condition you must remember, very dilute gives you hydrogen, dilute gives you NO. Right? All these HNO3 reaction is very important, must take care of that. Note is what here, important point. Beryllium is inert towards HNO3, it does not react with it. Write down. And this we call it as, it is rendered passive, right? It goes passive with it. So beryllium is inert towards concentrated HNO3 okay, towards concentrated HNO3. Reason is again the same thing. HNO3 is a strong oxidizing agent and it forms a layer of an oxide on the surface of beryllium. Further reaction is not possible. Okay, so barium does not react with it. Next point. Beryllium is amphoteric in nature. Beryllium is amphoteric in nature. Beryllium is amphoteric in nature. Amphoteric means what? Anybody? What do you mean by amphoteric? No. Yes, you can say like that. Amphoteric means it reacts with both acid and base. So you can say both types of characteristics it has, right? So beryllium is amphoteric in nature, right? It reacts with base, like for example, you see Na plus NaOH, we have a base, 2NaOH plus beryllium in presence of water, it forms sodium berylate. Sodium berylate, the molecule is this Na2BeO2 dot 2H2O, and H2 releases. If you look at the structure here, Na2 we have, and Be will have 4OH associated like this plus H2. This or this, anyone you can write on this product or this product. Done? Okay, one last thing you write down before the break. Solution in liquid ammonia, very similar to the previous one, that is group 1 element. Write down. Like alkali metals, alkaline earth metals except beryllium. Okay, alkaline earth metal like alkali metals, alkaline earth metals except beryllium dissolved in liquid ammonia, and gives blue colored solution, dissolves in liquid ammonia and gives blue colored solution, which contains solvated electrons, So reaction is metal, which is not beryllium, obviously, X plus 2Y NH3 converts into MNH3 X2 plus electron, which is surrounded by ammonia, and we call it as solvated electron, 2E minus. Okay, so because of this only, it shows blue color. Okay, this is the same thing. We have blue color solution and solvated ammonia, same thing. One note in this you write down: magnesium does not dissolve in liquid ammonia. Magnesium does not dissolve in liquid ammonia, but on long heating, hydrogen gas evolves. But on long heating, hydrogen gas evolves. Okay, that is it. So after the break, we'll start with oxides and few properties of oxides, hydroxides, carbonates, carbides. These compounds we'll see. So we'll finish off all these things today itself. Okay. After this, we'll have a few things on left. No, we'll see that also later on. Okay. Fine. So we'll take a break now. We have done a lot of theory. That's why I'm taking a break a bit early. Okay. We'll resume at 6:20. Yeah. Take a break, guys.